All right, it's 3 p.m. So we start our class in computer and network security. And this week we focus on secure hash functions and symmetric cryptography. And just as part of recapitulation, so let me remove this from the screen. So let us talk about security services as we discussed last time. So security services that could be provided using cryptographic primitives. So we have our information that we want to protect, and what kind of information it can be. It can be a file, and again, a file can be any kind of file. It can be a textual file, it can be a piece of software like Linux or Windows distribution, or anything you can think about, a picture, a JPEG file. And you want to protect it from different malicious attacks. And depending on the threat.
Okej, målet är ni att se till vilka som kan vara imorgon. Vi behöver inte gå in i detaljer, men
vi hör någon.
Till exempel för mig hela dagen, men kanske vissa kan...
Ni mutar. Okej, jag mutar honom. Okej. Jag ursäktar för oväntad brus. But nevertheless, so we talk about information and possible threats, external threats. So what kind of threats it can be? So, for example, somebody want to disclose the information, so get an unauthorized access to. So simply said, to read a file which this person doesn't supposed to read. In this case, we talk about confidentiality threats, and we want to provide confidentiality. What else? This information can be, for example, a payment order. So an electronic payment order issued, for example, in the context of Bitcoin currency. And in this case, one possible attack would be to deny creation of such information. And security services, to prevent denial of this kind of act, is called non-repudiation service. So basically, you want to sign the message electronically such that anybody can verify that it is that a particular user has created this piece of information. Another possible threat is that you receive a piece of information from an unintended source. So from an unintended actor, partner. And in these threats, or to prevent this threat, you want to be sure that the information comes from the correct user. So we are talking about authentication, so that the message comes from the legitimate party. And finally, the information that you that you create can be modified intentionally, or in the context of this course we are talking about unintentionally, or in the context of this course we are talking about intentional modifications of information. What can it be? For example, two use cases can come to my mind. First, you create, again, a payment order, so for a certain amount, for the certain amount of money, and a third party third-party agent takes your message and modifies the amount. So instead of, say, 1,000 kronas, it adds another zero to it. So you want to be sure that the information which is communicated between two parties was not modified on the fly, and while communicated. And here we are talking about providing integrity. So today we will be talking about very important security primitive building block for a building block for several of these services, specifically for building an authentication service, integrity service, and possibly even confidentiality service. And we will be talking about something which is called one-way hash functions. A synonym to this building block is also, sometimes you also hear the term secure hash functions. And today we will look at the main principles on how they are created and understand their main properties. So basically the one-way property and the collision resistance property, as well as we will see typical usages of secure hash functions. So first and foremost, so maybe you had math classes long time ago, but to recapitulate main definitions. So we start with the basic definition of a function. What is a function? So in mathematics, a function from a set of values x to a set of value y is such a rule that assigns each element of set y to each element of set x. So it is exemplified on this slide. So for example, our set x is all possible names of people in a country, and set y is our corresponding personal numbers, so date of birth and some codes at the end. So and there is obviously a function that maps a particular person with name surname to a corresponding personal number. So and informally talking, so we are talking about a rule or rules that define the relationship between one variable, so in this case, name of a person, and another variable, in this case, personal number. And by the way, you can interrupt me at any time. So I also see your messages in the chat if you have questions. Right. But today we will be talking about a very special kind of functions, which are also called hash functions. So what is a hash function? Hash function, well, basically is a rule. So in the terminology I presented before, that maps arbitrary size data to a fixed size data. So what do I mean? So on the left-hand side, so this blue, the blue boxes, they show the names. Well, in general case, it can be any or a string of characters of a variable length. So the names can be shorter, the names can be smaller, so it's very hard to probably define a typical size of the name. So we just have to live with it that the names can be of variable size, but we want to have a mapping rule that map any possible name from this set to a fixed size output. So, and fixed size, we define the size beforehand. So we say we want our output to be, say, 100 bits and not more than that and not less than that. So it is fixed size. Why do we need it? Because, well, there is a practical reason for that. It is very hard to work to create a software with tags of variable length. So we want to create a tag or a token which can be used in many contexts. And this token will be independent on the actual size of the original input. But at the same time, it can characterize the original input uniquely. A simple example of a hash function would be a modulus. So do you remember modulus from your high school classes or university classes? I hope so. So basically you have a target domain, say 1000. So all integers from 0 to 999. And then, so you basically can wrap around any number into and fit it in the range between 0 and 1000. So, this is mathematically reflected by this equation. So you take, say, what can be, as an example, variable x you set to 1005, and so it's definitely larger than 1000. So you basically wrap around this number, and it will be what 5. So 1005 model 1000 would be 5. And you can mathematically do algebraic operations with this type of function. So model 1000. We will be talking about it. So it is used quite a lot with in the context of encryption techniques that we will be talking about tomorrow, and also during the next theoretical module on public key encryption techniques. But for now, it's important to understand that we have a function, so a mapping rule that maps variables or values of a variable length into output of a fixed length. So this is our hash function. So let's talk about first about applications of hash functions in security before we actually add extra requirements on the type of hash functions that are needed. So remember, based on our definition, so we want to create a fixed size token. And this token relates to the original input. So it can be a file, or it can be, well, any string of characters, as I said. But the result is a fixed size digital token. So what can we do with this token? We can use it for integrity verification, meaning that hopefully, so if we use the correct hash function, then when we modify the input very little, then it will result in a different value of a hash. So we can understand that something doesn't work. So we have our token, we have our input value. So we compute the token ourselves. We check if the supplied token equals to the one we compute, and by if these two coincide, then everything is fine. So the information wasn't modified. If the token is different, then something is wrong. Something bad happened to our information during the act of communication. What else? We can, for example, do password verification. So this is a technique, rather old technique, which is used in Linux systems to store passwords in the file system. So obviously, passwords are tokens for personal authentication to a computing device, to a computer. And part of this information you supply when typing the password, and then it needs to be verified against a stored password in the system. And obviously, it is very insecure to store passwords in a clear text. So instead, what you can do, you can, again, for any input, you can create a token or alternatively, these tokens are called digests. You can create a digest of the input, and you want to store the digest instead of the clear text. What can you do more with such digests? For example, you can do trusted timestamping. So you want to timestamp the origin of the information. So you create a document, and you want to prove that it was created on a certain date. And obviously, here we come to the obvious need for the mapping of large size inputs to smaller size tokens, because of practical reasons. It's easier to store them, and cheaper to store, and easier to navigate through this database of timestamps compared to the verification of entire documents, for example. Another application of hash functions in security include message authentication. So this is specifically important in the context of secure communications over the internet. Later on, we will be talking about virtual private networks in the context of the network security. And in virtual private networks, so you want to be sure that the stream of data between your machine and the server happen without intervention by a third party, by an attacker. So nobody modifies. Yes, I will attend now your question, okay. Nobody modifies your informations that you communicate in packets in between. And moreover, finally, you will see how hash functions can be used to encrypt data. So let me see, we have a question in the chat. All tokens created has a fixed size. Does it mean that there are a finite number of possible tokens? Absolutely. There is a finite number of possible tokens. I will now extend this answer after I read and answer Max question. I don't understand how Um, no, no. Actually, that's a valid question. So uh, this example is about principles of a hash function. So in this case, you want uh, you want the results to be within a certain fixed range. So it's probably was incorrect talking about this example in the context of the of obtaining fixed size. So um, so so look at back to your question. Yes, the number of tokens is finite, but they are astronomically many. For starters. But now we will be talking about also other properties of the secure hash functions. I will demonstrate the problem of collisions of hash functions. But we are talking about computing a token of a size of size 256 bits or 512 bits. It means that the total number of tokens would be 2 to the power of 256. So this number is astronomically large. So even 128 bit large number opens up for astronomically large number of variants. So it's comparable to the atoms in the observable universe. So let me see. Yeah, yeah, yeah. Yes. Yeah, that's it. So basically, so the size of the target space of this set. So the number of possible elements of Y set is extremely large. But the important point is that the size of each item is smaller than the size of items in the original domain here, X. And again, so one simple example, you take the entire Windows distribution with all these gigabytes of code or compiled code, and you apply, you run it through a hash function, and you get a 256 bit token. So on the one hand, you had a domain, a set with entities which are can be gigabytes long, and on the other hand, you have tokens of 256 bits. Um, so let me show you now the main principle of computing or constructing a hash. And then I want to show you a somewhat naive approach to creating a hash. And based on this example, I will demonstrate the principle of collision. Well, the principle of collision is already demonstrated here on this slide. Basically, two distinct inputs when running through the hash function would produce the same result. And this is something we really don't want to have in the security domain because, well, as I will summarize later on, we want to have such a hash function that even if you change a single bit of data in the input, you will get a totally different output. And this is possible exactly because of the number of variants you may have in this target domain. So, but you simply want to create such a function that for any modification of the input would result in generating totally different output. But let me switch to, or not to switch. I will bring my handwriting tool if my computer will cooperate with me. By the way, about observable number of atoms in the universe, is it? I mean, where did you get it from? Is it from the course on computer networks? Yeah. Ah, okay. Yes, because I no, normally this example comes along the with the motivation of uh, changing IP protocol, internet protocol from version 4 to version 6. So where the main difference is in the size of the address space. So 32 bits in IP version 4 versus 128 bits in IP version 6. And it is there. So this is the main motivating factor that with 128 bits, you can assign an IP address to all basically atoms in the universe. So that's why I'm asking you this question. Just give me a second. Yes. All right. So let me sketch a general approach to creating a hash function. So, I will upload PDF with my handwritten notes to Canvas after the class. Algorithm. So what do you have as an input? You have your original message. So of arbitrary size. And the first thing you do, you split it into chunks of the desired size. So this is your target size L. So which can be, say, 256 bits, even 128 bits in certain algorithms, 512, 384, 128, many of them. So the first hash functions, they produce 264-bit outputs. But the principle is pretty much same. So you split it into chunks of fixed length. And let's call them M1, M2. And finally, you have maybe MN. And if this chunk is the last piece of data, uh, if it is smaller than the target size L, then normally you apply padding. Yes, and the main principle. So, this has even its own name. You will see it on the slide later on. Is uh, to stack execution of the digest algorithm, uh, which taking each block, each chunk at a time, and mixing up with the previous result. So so you have your digest algorithm. So now we will start with the very naive one. So you input, normally you initialize it with some constant initialization. So you put first message chunk, so you produce output of the target size, and you input it to the next iteration of the same algorithm. So digest. And you mix it with the next block, and so on and so forth. Sometimes you even run several iterations of the algorithm. Yes, and at the end you produce so digest of size L. Right. Digest. So what do you do with the digest? It's a this is your token, and you which you want to use for integrity, whatever purposes that I described before. So it means that you append this token to the main message. So you put your digest over here. And so now you associate the digest to the information that you protect. So I hope that this main principle is clear. So we didn't look inside the algorithm, and we won't go into details of the real algorithms. I just want to sketch a very simple hash function that satisfies the property of mapping variable size input into the digest of a fixed size, and we will study its properties and see what can be wrong with the proposed approach. So So let's construct our hash function using the following binary operation. So we talk about protecting digital information in digital form. So at the end, I mean, for computers, it boils down to operate with the zeros and ones, and to information. So that would be our first step to binary representation. And then hash function will be constructed using binary operations. Using binary operations. So all these binary operations are known to you. So let us see what we can do here. So if we have two variables x and y, so what we can do AND. So binary or logical AND. I will list them first, and then I give you example of those operations that we will use. Another operation could be OR x. So this is OR. And then what could be needed is something which is called exclusive OR x. So it is denoted like this, plus y. So this is exclusive or XOR. In other words, and there are other several other operations like taking a complement or inverting all the bit positions. But I will construct a hash function using XOR operation and operation of shifting. So you can take, for example, X and shift number of times. So this is circular shift. Circular shift. So let's focus on these two guys. It's very simple operation. So exclusive OR. So if you have uh, if you write the truth table, so the result of the operation, so it's and if you take bit one, so it's a bitwise operations. So you take bit one, you XOR with 1, you get 0. You take bit 1 XOR with 0, you get 1. You get 0 plus 1 is 1, and 0 XOR 0 is 0. So basically, if you have two if you apply operations to the same value of the bit, then it will result in 0. Yes. Exactly. Hmm. So, and I will tell you also the why would we want to use it a little bit later. So nothing to be stressed about remembering. Just I mean, take it as a curious information. Another operation I want to use is this circular shift. So if you take so this was XOR. And so the circular shift, so for example, for binary string, uh, say 1 0 1 0 0 1. So shifting it uh, one time. So you basically take the last one and put it in the first position. So the first position goes to the second position, and so on and so forth. So this is circular shift. So obviously, so you can apply this operation several times. Then so you would rotate. So again, the following. So let me see. So the following information that I will tell you now is again for your general knowledge, but these two operations have very interesting properties. So if you take, for example, two randomly generated bit strings uh, and you XOR them together, then the result of XORing would appear as a random as yet another random number. So on when the size of the bit sequence is sufficiently large. The same goes for the shift operation. So if you take randomly generated string of zeros and ones, you shift it and you compare the two sequences, so they will appear as random with respect to each other, and this is a very good desired property because we want to randomize our input. But again, so this is nothing to remember. I mean, this mathematical property. But just to say that it's not by chance I chose this XOR and shift operations. So now our uh, naive hash function will take the following form. So hash 2. So we have our, remember, so this is our message, and we split it into 1, 2, and so no padding, just assume that we have it this way. So we will construct, and maybe for simplicity, so let's have finite number of chunks. So 3. Message is split into 3 chunks. All right. So our hash function, so we will define it like this. So we take first chunk M1, we shift it. So yeah, again, so remember that this is shift. And now, I mean, all this MI are binary. So zeros and ones. So we will construct our hash function like this. So again, according to this principle that I outlined here. So you take M1, so basically your hash function would be shifting and mixing up with the new chunk would be XOR. So you take XOR M2, so then the result you will shift and mix up with M3. So it's quite simple. Do you follow me here? So M1, M2, M3 are binary chunks of certain size. So let's have it, for example, 8 bits, so like 1 byte each. So what you do, you take each chunk. So your digest function then is shift. So you circularly shift a chunk, and then you on the next iteration you mix the result with the next block by XORing. And so you take now the whole result, and so on and so forth. So you build a chain of these operations, and at the end you obtain your um, H1. So let's denote it as H1. So what can you do with it with this H1? So we focus now on using this hash for integrity verification of the original message, so that we want to use this value. Well, before all, it's a proper hash. So why? Because it takes a variable length message and it produces a fixed size result. So do you see why? Because the result of all this operation, so this H1 is fixed size. So, you know, yeah. So you take chunks of the same size, and you apply bitwise operation, so you don't expand. You don't expand your result. So H1 is exactly size L. So now you append H1 to the message, and this is H1. And you say, okay, now this is a hash of my message, and I want to use it for integrity check. So can we use it for integrity check? So can we modify the message such that um, that the hash function will always be different for the modified message? Well, apparently, it is quite difficult if you don't um, expand the message itself. Because so all these operations, this shift and XOR, they are modular operations. So you wrap around. So it's very hard to keep track of bit changes. I mean, the more bits you apply. But at the same time, so this hash function has a very serious flow. So what I will show you now, so we will perform an attack by constructing a new message prime. So that when you compute h, let's call it h prime, it will be exactly same as h1. So meaning that we cannot use function in this way for security purposes. So let us think how we can do that. As I said, if you if you do not expand anything, well, if you do not expand the original message, it is quite tricky to figure out what bits has to have to be changed within the message, such that the resulting hash function will be exactly the same as the previous one. But we can do something different, and that is what is typically called a concatenation attack. So we will see this attack applicable also in the context of message authentication, constructing message authentication codes for internet packets soon. So what we can do, we can expand the message in a certain way, such that at the end we will have the same result. And how do I mean this? So let me take now this result, so which is essentially is the hash one. And remember, so in the security services, H1 is communicated in clear text as well as the message. So you have both the message and the hash of the message. So this is this two pieces of information are always available to you. So. But now what you want, when you construct your message prime, so you take, so let me see, so that will be your message prime. So you take the original message, you add your stuff. So, for example, if this was your payment order with a sum towards the end, so you just stuff more zeros here, for example. So, and we will add a single message, message 4, and then we will add something else, so that the result of the calculations will be exactly h1. And again, so this function is very simple. So this part, when if you would take the original message and add a new block, new data block to it, it will result obviously in a new hash value. So essentially, you take this this equation. So let me mark it as star. So you take star, and again, so the function is known. So you always supply this information as part of the communication process. So because in order to verify something, you need to know what algorithm was used for creation of the token. So you take this original, so you start to compute the function, and you come to the point you computed this hash function, the old one. Then you continue computation. So you shift this value and mix up with M4. And this thing obviously will produce a new hash value, H new, right? Which is different from H1. But again, so the long story short, knowing the algorithm and this naive way of constructing hash function, you can construct a simple equation. So you take so let me just maybe do like this. So you take H new, you want to add a new block to it. So when computing the hash function with this new block would result in H1. And this is a simple equation. I mean, taking into account the binary operations that we use. So this is very easy to compute, knowing all these operations. So you take basically XOR with the shifted of the shifted new value of the hash with the target H1, and the result will be this target new block. And what we did, so we extended the message with our malicious information and some extra information which maybe doesn't make sense. I mean, for the application, but so it just exists as a sequence of bits. But what we achieved is that using this hash function, we created two messages with the same hash. And apparently this is really, really bad. So it means that these functions are not good for providing security services. Do you have questions about this example? First question, do we have to calculate those in quiz? Not for the hash, not for the hash part. Just know the general logic. So explaining it again. So now when we have everything written, so let me briefly summarize it. So we started by chopping the original message into number of blocks. In our case, 3 blocks, M1, M2, M3, of size L bits. Okay, so we have 3 chunks by L bits. And then I proposed the following hash function. So you take each chunk, you circularly shift. So in this manner over here. So you take the last bit to put it on the first position, and then shift all the bits to the next position. So this just one of the valid binary operations. And following the general logic of constructing hash functions, so we need to mix in the next blocks with the output of the hash function for the current block. And this you do with XOR operation. So here. And then again, so you take the result and you want to mix in the next block, M3. So for this, you shift the result and XOR M3. Okay. And then this will be your hash value. And then I showed you a possible attack to this scheme where we constructed a new message, message prime, such that the result of computation will be exactly same as for the original message. Let me sketch a simple example. So, for example, M1, we have 0, 1, 0, 1, 0, 1, 1, message 2, well, it can be anything, 0, 1, 1, 0, message 3 is 1, 0, 1, 0. So, okay. So, the first iteration of the digest algorithm, so we take M1 and shift it, circularly shift it. So what we get as a result, we get 1, 1, 0, 1. Okay. So you just put this one to this position, this one to this to this, etc. So on the next iteration, so what you do, so you mix in M2. So you take M1 shifted and do XOR with M2. So you take this value and XOR it with this value. So let's see if we don't, if it doesn't result in all zeros. So we have 0, 1 and 0. So that will be 1, 1, 1 on the second position will result in 0, 1, 0 on the third position result in 1, and 1, 0 will result again in 1. Okay? So on the next iteration, so before we mix in with M3, so we take the whole thing, so and shift it. So M1 shift XOR M2, and we shift it. So basically we do like this. So the result will be 1, 1, 0, 1. And now we mix in M3. So the final, so H1 is M1 shift, XOR 2 shift. I need to be careful with my writing, otherwise you won't parse it at the end. And you mix in M3. So so you take 1 and 1, 0, 1 and 0, 1, 0 and 1, 1 and 1 and 0, 1. So here it is, right? This is your hash function. And the original message is just all these three chunks concatenated, right? So now we want to add M4, so the attack part. So odd M4, which is, say, again, maybe you just duplicate the next, the last message. So 1010. Okay. So now you want to get H1. First, let's compute the new hash new. So for this, we need to shift the old, the previous value. So we continue calculations. So it will be basically H1 shift plus M4. So H1 shift, it will be 1 0 1 1 XOR 1 0 1 0. So this is M4. So and our H new is then what 0 0 0 1. Are you with me here? So 1 XOR 1 is 0, 0 XOR 0 is 0, 1 XOR 1 is 0, and 1 XOR 0 is 1. So this is your H new. And this is different. It is different from H1. So, I mean, you need to do something about it. So the attack is not complete. So you added a new block, you violated integrity of your message, and so it can be detected. It can be detected by the verifier. So it takes 4 blocks, computes this H new, and then it compares it to H1, which is communicated in the same message. Either in the same message or it's. I mean, you can get it as part of the certificate, for example. Um, so. So you need to do something about it. So that's not good. So this is your plan to take this H new. So do something with it so that the final result will be H1. And this doing something means that so you take this H new. And you want to add a new block that you will add to the main information, such that when you compute the function, will produce H1. So our algorithm is that this new block, I mean, for computing the hash value, so you will first shift the a result that you obtained after adding M4. So here you have malicious information. So the hash function will shift it, and then you will add, you will XOR with something. So, or let me say this. Let's put it as a question mark. So this is the equation to solve. And in the bit form, so now so this H new shift will be, so you put 1 here and shift all zeros there. So it's 1 0 0 0 XOR with something that is equal to the value that you want to get you want to obtain at the end, which is 0 1 1 1. And this is a XOR operation. So, you to solve this equation, you XOR these two numbers basically. And the result then, so your question mark is a block which looks like this. So it's one, so all ones. Okay. So if you add all ones to this 1000, you will get 0111, which is the valid H1 function, the valid output of the H1 function, of the original hash, sorry. Okay. And that means that you need to put this block as this is your M5. So your modified message would be M1, M2, M3 with M4 with your malicious information and M5 just to make it make all the computations correct. That the result is the hash function. So you perform the attack. But this also this is a made up example. Simply shows that we need to put extra properties to the hash function so that if you change even a single bit, and not as we did here, like we added like two new blocks, the result of computation will be totally random output. So this is our requirement. So this is an example of something which is called a collision attack. So we found two messages producing the same hash value. So this is a hash collision. And this brings us to the very important property of collision resistance. Are you with me on this example? Okay, good, good. So I will upload PDF with the notes. So let's continue. And actually, to come up with such a hash function, it's well, it's a tricky business, so to say. Not impossible, but yes. Okay, so I'm reading the chat. Maybe when you do this exercise, comparing it to a real example, you can refer to this slide. So what would be what would be a possible attack? So maybe that's what you're trying to do, Tony, here. So, for example, you have certificates. So you log into a bank, but an attacker want you to redirect to a wrong website. And it uses a certificate from your bank so that when you verify it with with the hash function, so it will give you correct output. I mean, it will say that the attacker website is the valid bank website. So this is one possible analogy in the real world of this type of attack. Or think about distribution of a software, say a Windows. So so on the Windows website, so you have they publish their hash values, and then you get your software via, I don't know. So when downloading, you download it from some mirror on which somebody put a modified version of this distribution. And again, so it is extremely important to detect that the software that you download actually was modified. So basically, we want to prevent these attacks from happening, the one that I sketched previously. Did I answer your question, Tony? Yeah, good, good. But the good news that uh, Many such examples. Sorry for saying rubbish. Um, So there were several cases demonstrating that collision attacks on hash functions, on hash algorithms, are feasible. However, the practical importance of these attacks, it is rather questionable. So to perform these attacks, you need to do quite extensive search. And in many cases, so the feasibility of such attacks are boils down to constructing toy examples. I mean, just one example for which it works for a given algorithm. It's not that. So basically, what I want to say is that these two attacks that I outlined here, they're extremely difficult to perform. So just to take somebody's certificate and uh, find such certificate changes that it results in the same hash function, that's computationally very difficult. But all this attack that I presented to you highlight a very important property that secure hash functions have to satisfy. They need to be collision resistant. So, in other words, it is difficult to find two messages that produce same hash. Well, there is a more formal definition or even stronger definition of such properties. Secure hash functions, they have to produce output with very strict properties or on the pattern of zeros and ones. So they need to appear, so the output of a hash function need to appear as totally random sequence. Informally speaking, it means that the number of zeros and number of ones should be approximately be same. So in a given size sequence, and importantly, that the input and output should be totally uncorrelated. So a single bit change would result in a totally random pattern. So that's how it works. So let's see this property. I mean, um, if we can find evidences of such properties in using real hash functions. And real hash functions, there are several. Well, let me first show you the slide with the names of such functions. So you all seen them in your day-to-day life. So I understood last time. So you all worked with software in one way or another, and so you basically, I bet that you met several times such a name as MD5, for example. So MD5 hash. So if not, so again, so if you try to download Windows, so it normally or any other software package, it normally goes with this MD5 hash or SHA hash. So these are the names of popular secure one-way hash functions. So those are. Okay. Yeah, but MD5 was basically the first hash function to appear, so it was developed by the same people who developed RSA, public key encryption algorithms. Uh, uh, but the other alternatives, so they known as secure hash algorithm (SHA). So the widely used hashes are SHA 256, 384, etc. So you will see them in during practice when you will decode certificate from a website. So you will see different functions. But again, so the type of algorithm is always supplied, is always given to you. So because you need it for verification purposes. But and all operating systems. So let me see if I manage to make it larger here. Maybe. Yes. So they have set of functions uh, to perform these computations. So let me see. So I have created a file, so which is called test. So let me see what's inside. No, it's just hello world textual file. And what I want to show you. So let's see MD5 head function MD5 sum test txt. So MD5 produces hash of size 128 bits. So this is the hexadecimal value of the result. So now let's see what will be the output if we change one letter. So it's not a bit; it's the whole character, so which is 1 byte. So say we change E to A. So let's double check if we have changed it. Yes. Q. So and let's run MD5 again. So you see, so we changing a single character, so it results in a totally different hash value. Moreover, so you can even think of opening this text file in the binary format and modifying a single bit yeah, in it, and then you also can what you can do so you can convert these values to binary and see that in binary, so they're totally random sequences of zeros and ones. All right. In addition to operating system commands, and again, so they are they can differ from operating system to operating system. So, for example, I use Mac, Mac OS, and here we oh, is it? So here we have a different command. So, for example, so in Mac, so it's not MD5 sum, it's just MD5. Yes, but they also should produce same values, obviously. All right, so let's see how we're doing here. Yes, I'm finishing very, very soon. The common thing to so all these different hash functions, MD5, which stands for message digest, SHA, so of different sizes. So they follow all the same principle as I have outlined previously. So which also has a name. So this algorithm has a name, Merkel-Damgard principle. Which basically has the algorithm, the hash algorithm, and then it mixes in new chunks of original information, and at the end produces the hash result. So a useful library that you can use, I mean, when programming, for example, secure applications, is OpenSSL. In OpenSSL package, you have all these implementations as well. So the format is slightly different, but they do the same job, basically. Same algorithms exist in different language-specific uh, environments, like in the SQL databases. So you can call for hash function execution as part of your SQL query in Python, C, so you can use these algorithms connecting appropriate libraries. Yes. So let us talk now about the applications of one-way hash functions uh, quickly. Integrity verification, so that what we have covered so far, so that's quite straightforward. So now with secure hash functions, so we are on the safe side. So we can use it to verify that nobody has interfered with our data. One interesting use case uh, is using hash functions for storage of passwords. So again, that's specific for Linux systems, and where all passwords are saved in a shadow file, etc. shadow. Oh, ah, yes, that's the shadow. No, yes, I need a root access to it. Uh, So here, for example, if you scroll and find entries for specific users, so here the name of the user is seed, so then you see this string of characters where this 6 indicates the type of the hash value that was used to create to compute the hash. Then normally you have some characters for initialization value. So I think it's until the next dollar sign. So this value is called salt, and this value is used to prevent attacks like dictionary attacks for password-based authentication systems. And after the dollar sign, you have the hash value produced with the given algorithm. And this is done with the obvious purpose not to store passwords in clear text. So you have only the hash, and it is one-way hash function, so you cannot take the value and decode the password, but it is useful for verifying the correctness of the password entered by the user. And then what I want to show you, yeah, so some other use cases you can read both on the book and in the slides that I skip now. Message authentication code. This is an important functionality in the context of the network security. Where you want to protect your communication against man-in-the-middle attack. And here well, previously when talking about integrity of information, I was talking about, modifying, for example, bank order. Here, I mean, what you can do, you can change, for example, control information in the IP packets, and in order to detect it, so you need to add um, uh, authentication code. In order to understand that the data comes from the legitimate party, you need to have a token attached to your packet that uh, um, you can use to verify that you talk to the right person. And this is also done using hash functions. So you take your package with all the information that you want to protect and compute a hash. But here you can read about a particular algorithm, which is hashmac, in the book. So I can only briefly comment on the reason for having this structure. So what you want to achieve, you want to ensure that that message M comes from person that you know. And the way to ensure it is to share a key. So here we don't talk about the way how you share the key. There are different schemes to do so. So one of the schemes we will look at during the public key crypto module. But assume that you share the key with your partner, and you want to you want to ensure that messages that you receive are really the messages that come from your from the partner you're expecting it to come from. And to do that, so you take your key, the secret key, and so append it to the message itself, run a hash value. You run a hash function, and then you kind of wrap this hash in another hash together with the key itself. And this value can be computed only if you by the partner who knows the correct hash. So you can check both the integrity and the that the person shares the key with you. All right. That is it. What I wanted to tell you about. Again, so please, if you have any questions, so now it's a good time to ask or talk about it. So if you have anything to say or comment, or if you want to know something more along these lines, so let me wait. Yes, Daniel, please.
Hi. If I understood it correctly, then in the hashed message, like after it's gone through the function, there should be an equal amount of ones and zeros.
Yes.
Okay.
Not equal, approximately equal, not strictly equal.
Right, but one where it's like 10 zeros and 2 ones would be a badly hashed message.
That's rather badly compound. So normally hash functions they produce good random outputs.
Okay, thank you.
But again, so this property may be not very kind of important practically. Just this property ensures that you cannot really take the message and by looking at the pattern of zeros and ones understand what bits were changed. So because I mean the opposite example would be okay. So you look at the legitimate hash. And then you see that if you modify this bit to 0, then three zeros appears along the way somewhere. So that's not desired behavior. So in this case, your hash function is correlates input with the output. So that's why I mentioned that the output should appear as a random sequence. So you shouldn't be able to track the changes in the output based on kind of controlled change in the input.
So it's kind of like you don't want there to be a clear frequency in a
No.
way.
Mm-mm, mm-mm.
Thanks.
All right. More questions? Well, you always can write your questions in the Discord. So whenever you have some, I will comment on the topic of the quiz tomorrow because I'm still kind of having last checks on the assignments. I will definitely tell you the time limits. You will be so the only thing I can tell you that I mean the time limit for a quiz is quite generous anyway. So compared to the time it would be needed to solve it. So, all right. Thanks for today. See you tomorrow. Have a good one.